Let's jump right in. You've shared some fascinating sources, and we're taking a deep dive today into what makes a computer processor tick and, well, more importantly, how its performance is really shaped. Think of this as getting a look under the hood of your digital world.
Exactly. We've got materials here that cover, the fundamental building blocks, how instructions get handled, and the key factors that really influence speed. Our goal is to pull out the most important insights, connect the dots, and give you a clearer picture of what's going on inside that chip without getting too bogged down.
Right. So if your computer speed sometimes feels a bit mysterious, this is your shortcut to understanding the engine. We'll start with the foundational elements, how memory is organized and how the processor talks to it using things called buses. Then we'll tackle the big levers of performance, clock speed, the number of cores, and cache memory. And finally, we'll look at a clever technique called pipelining that boosts efficiency. Understanding these basics is kind of like understanding the physics behind motion. It explains why things move the way they do. Here's where it gets really interesting. We've talked before about the fetch-execute cycle, that fundamental loop, right? Where the CPU grabs an instruction, figures out what it means, and then, boom, performs the action.
Yep, the core loop.
But how does it even access the instructions or the data it needs from memory to do all that?
Okay, yeah, that's where the physical structure really comes into play. The sources remind us that memory isn't just like one giant block of data. It's logically divided into these equal-sized units. They're called words.
Words. Okay, like pigeonholes in a massive filing cabinet. Is that a fair analogy?
That's a great way to think about it, precisely. And these word lengths, they're pretty standardized across different computer architectures. You usually see 8, 16, 32, or maybe 64 bits long.
And every single one of those words, those pigeonholes, has its own unique address, right?
Yes, exactly. A separate memory address, like a unique house number for each pigeonhole. And this addressing is absolutely fundamental because the processor needs to know exactly where to find a specific instruction or a piece of data.
Okay, so memory is organized, it's addressable. Got it. Now, how does the processor physically navigate this vast filing cabinet and pull out the right word?
Well, that's the job of the buses. Basically, they're bundles of wires on the motherboard. You have the address bus first, its main role, to carry the memory address from the processor to the memory controller.
So the processor shouts out, "Go fetch from address 1234 down the address bus."
Pretty much, yeah. And the crucial point here, the really important thing, is the width of this bus. That means the number of separate lines or wires it has. That width directly dictates the maximum number of unique memory addresses the whole system can possibly access. It sets a hard limit.
Ah. Give us the example from the sources. That really makes it click.
Okay, so the sources show that an 8-bit address bus, just 8 wires, can access 2 to the power of 8 addresses. That's only 256 unique addresses.
256, that's tiny in today's world.
Right. Now, compare that to a typical modern PC. It might have, say, 4 gig of memory, gigabytes.
And 4GB is way, way more than 256 addresses.
Oh, exponentially more. See, 4 gig is actually 2 to the power of 32 bytes. So to even see all of that memory, let alone address each byte or word individually, the system needs at least a 32-bit address bus.
Wow.
So the bus width isn't just about speed, it's a hard physical limit on how much memory your system can even use. That's a pretty fundamental constraint, you know?
Okay, wow. So a narrow address bus doesn't just slow things down. It literally blinds the processor to memory
Yeah.
beyond a certain point. That's fascinating. What about the data itself? How does that travel back and forth?
Right, that's the other main bus, the data bus. Now, unlike the address bus, which is mostly one-way traffic processor to memory, the data bus is bidirectional. Data travels both the memory and from memory along these lines.
And I'm guessing its width matters too.
Absolutely. Its width defines how many bits of data can be transferred all at once, simultaneously in a single operation. And here's a key efficiency point. If the data bus is the same width as a computer word, let's say you have a 64-bit wide data bus transferring 64-bit words, the processor can fetch or store an entire word in one go. One clock cycle for the transfer.
Makes sense.
But if the bus were narrower, say only 32 bits wide, trying to move a 64-bit word, it would have to break the word into smaller pieces, 2 transfers instead of 1. That obviously takes longer.
Okay, so we've got memory organized into words, address buses to point to the right location, and data buses to move the actual bits. Now, how do the instructions themselves fit into this picture? We hear about assembly language and machine code.
Yeah, assembly language is a very low-level language. It's incredibly close to the raw binary machine code that the processor actually understands. Often there's almost a one-to-one mapping between an assembly instruction like, say, load this value, and its machine code equivalent, the actual zeros and ones.
And the format of that machine code instruction, how it's laid out in binary, that's not just random, is it?
Not at all. It's fundamentally determined by the computer's architecture. Things like the word size we just talked about, and critically, the width of the address bus.
Wait, hang on. The address width affects the instruction format itself. Why?
Because think about it, many instructions need to include an address as part of the instruction, like load the value from memory address X. So the maximum size of the address you can even specify within that instruction is limited by how many addresses the bus can reach. If your address bus is 32 bits wide, you need enough space in your instruction format to potentially hold any 32-bit address.
Okay.
This dictates how many bits the operand part of the instruction, the part specifying the data or address, can use.
Okay, that clicks. The instruction needs enough room built in to specify any possible address the bus can actually get to. The sources give that example right. The hexadecimal C50D.
Yeah, exactly. That's shown as a raw machine code instruction. And it means something like load the contents of the accumulator register into memory location 0B, or maybe an assembly equivalent like LDA #13. You can see how the binary pattern of C50D would have to encode both the operation, the load part, and the operand, the address or value, 0B or 13 in this case.
So that's the bedrock. Memory structure, buses moving data and addresses around, and instructions formatted based on all that underlying architecture.
Got it. Now let's shift gears to the big three, the main factors the sources identify that really affect how fast a processor performs once it, actually has an instruction to work on.
Right, these are the ones everyone talks about when buying a computer. Clock speed, number of cores, and cache memory.
Okay, let's start with clock speed. We see numbers like 4 gigahertz, 5 gigahertz bandied about. What's physically happening there? What does that mean? Okay, think of the system clock as, like, the metronome or the conductor of an orchestra. It provides a perfectly regular series of electrical pulses. O and off, O and off. Every single operation inside the processor, including each tiny step of the fetch-execute cycle, is synchronized to these pulses. It basically tells everything when to take the next step.
So the faster the pulses, the faster the ticking.
The faster the processor can potentially move through each stage of fetching, decoding, and executing instructions.
Yeah. And these pulses happen incredibly fast. We're talking billions of times per second. Like the source notes, a 4 gigahertz processor is ticking 4 billion times every single second.
That's just a mind-bending scale to think about. Okay, second factor, the number of cores. This was a huge shift in processor design, wasn't it?
Absolutely huge.
Yeah.
Instead of just one central processing unit doing everything, many modern chips have multiple cores, like multiple brains built right onto the same piece of silicon. You see dual-core, quad-core, octa-core, even many-core processors now.
And the key idea behind that is parallel processing, doing things at the same time. Precisely. Each core is essentially a semi-independent processor. It has its own registers, its own connection to ports of the cache, and it can run its own fetch-execute cycle. This allows the chip potentially to work on multiple instructions or even multiple parts of the same larger task simultaneously. That's parallel processing or concurrent processing.
So theoretically then, a quad-core processor could finish a certain kind of task 4 times faster than a single core.
In theory, yes. For tasks that can be perfectly split up into 4 independent chunks and run without interfering with each other. But, and this is the crucial nuance, the sources highlight many software programs and even parts of the operating system itself aren't always written to effectively distribute the workload across all those cores.
Wow.
Instructions often still need to be processed sequentially, one after the other, because one depends on the result of the previous one. So while the potential for a 2- or 4-fold speedup is there, you often don't actually see that full linear increase in real-world performance. The software just isn't always designed to fully leverage all those cores effectively.
That explains a lot. It explains why some modern applications feel lightning fast on a multi-core chip, but maybe older software or certain types of tasks don't seem that much quicker.
Yeah.
Okay. All right, the third big one, cache memory. What's the story here?
Okay, cache. Cache is essentially a very small, incredibly fast, and also quite expensive type of memory that sits right on the processor chip itself, physically very close to the cores.
So it's much, much closer and faster to access than the main system RAM chips on the motherboard.
Oh, orders of magnitude faster. Its whole purpose is to act as a temporary holding area, like a super fast buffer, for instructions and data that the processor has used very recently or is statistically likely to need again very, very soon. The idea is to avoid the delay, the latency of having to go all the way out to the slower main memory every single time it needs something.
And there are different levels of cache, L1, L2.
Yep. The sources mention level 1, L1, and level 2, L2. L1 is the absolute fastest and smallest, often measured in just kilobytes. It's usually private to each core. L2 is larger, maybe measured in megabytes, but slightly slower than L1. It might be private per core, sometimes shared between a couple of cores. And many modern processors also have an even larger, but slightly slower still, level 3, L3 cache that's shared by all the cores on the chip.
And the L1 cache often has another split inside it, right?
Often, yes. It's frequently split into an instruction cache, I cache, and a data cache, D cache. This allows the processor's different units to look for the next instruction in the I cache at the same time as it's fetching or storing the data needed for the current instruction from the D cache. It avoids them tripping over each other, basically. Further reduces bottlenecks.
So what's the bottom line benefit of having more cache? If I see a processor advertised with more megabytes of cache, what does that mean for me?
Well, the bigger the cache and the smarter its management, the higher the probability that when the processor needs the next piece of data or the next instruction, it's already sitting right there in that super fast cache. That's called a cache hit. Getting a hit is great. It means the processor doesn't have to pause and wait for the data to arrive from the much slower main RAM. So more cache generally means more hits, less waiting, and significantly faster overall operation. It keeps the processor fed and busy.
Okay, that makes sense. So clock speed sets the raw pace, the tempo. Cores add the potential for parallel work, doing multiple things at once. And cache acts like a super fast pantry right next to the cores, keeping them from waiting on deliveries from the main memory warehouse.
That's a pretty good summary, yeah. Those are the main drivers.
But the sources also mention pipelining as another technique. How does that fit into boosting performance? Is it separate from those three?
Pipelining is more of an efficiency technique, a way of organizing the work within a core to get more done in the same amount of time. It allows the processor to work on multiple instructions at the same time by overlapping their execution stages.
Overlapping, like an assembly line in a factory.
That's the classic analogy, and it works perfectly here. Instead of waiting for one instruction to go through all the stages of the fetch-execute cycle, like fetch, decode, execute, write back, before starting the very next instruction, pipelining breaks that cycle down into distinct stages. As soon as instruction A finishes the fetch stage and moves to decode, the pipeline can immediately start fetching instruction B.
Ah, so while A is being decoded, B can be fetched simultaneously.
Exactly. And then while A moves to execute and B moves to decode, instruction C can enter the pipeline and start being fetched. You have multiple instructions all in different stages of processing moving through the pipeline concurrently. The sources note that modern pipelines can have many stages, sometimes 10 or 12 or even, 20 or more in really complex designs.
Wow, so this doesn't make any single instruction execute faster from start to finish.
Correct. The time for one instruction to pass through all stages, the latency, might even slightly increase because of the overhead of managing the pipeline stages.
Right.
But it dramatically increases the throughput, the number of instructions that can be completed per clock cycle on average. Once the pipeline is full, ideally you're finishing one instruction almost every clock tick. It keeps the instruction stream flowing much faster overall.
That's really clever. It's maximizing the rate of completion, the throughput, rather than minimizing the time for just one task.
Precisely. It's all about keeping all parts of the processor busy as much as possible.
Okay, so we've covered a lot. We've laid the groundwork with memory words and buses, seen how instructions are actually formatted based on that architecture, explored the big three performance factors, clock speed, cores, and cache, and now looked at pipelining for internal efficiency. How does understanding all of this actually connect back to you, the listener, and the computer you use every day? What's the practical takeaway?
Well, it directly impacts pretty much everything you experience. How responsive your computer feels, how quickly your applications load, how smoothly you can multitask between different programs. A higher clock speed generally means faster individual operations. More cores offer the potential for smoother multitasking or faster performance in software that's actually written to use them properly. And faster cache means the processor spends much less time just waiting around for data, which is often a massive performance bottleneck.
Right. So when an application feels sluggish, or maybe when trying to run two heavy programs at once, brings your machine to a crawl, it often comes back to one or more of these core limitations. It could be the raw clock speed isn't high enough, or the software isn't using all your cores effectively, or the cache isn't big or fast enough to keep the processor fed with the data it needs right now.
Exactly.
And that helps explain why, say, just adding more RAM sometimes helps if you were genuinely running out of memory space, but it won't magically fix a bottleneck caused by the processor's fundamental speed, or its core count relative to the software, or its cache performance.
They all work together. Absolutely. It's a system. But understanding these main factors, clock, cores, cache, and how things like buses and pipelining enable it all helps demystify where that performance actually comes from and why different computers or even the same computer running different software can feel so vastly different.
So wrapping up, we've seen how that foundational structure, the memory organization and the bus system, enables the processor to even get the data and instructions it needs. And then we saw how clock speed sets the basic tempo, multiple cores offer that potential for doing work in parallel, and cache memory acts as that critical high-speed buffer. All are really crucial dials influencing performance.
Hmm. And techniques like pipelining add another layer, squeezing more efficiency out of each clock cycle by keeping the instruction stream flowing. It's a really complex balancing act of speed, capacity, and just clever internal organization.
So if the speed and responsiveness you experience on your computer are the result of this incredibly intricate dance, billions of clock cycles per second, the software challenge of actually using multiple processing units effectively, the sophisticated caching of frequently needed information, what does that tell us about the continuous engineering challenge? Making processors faster, more efficient, especially when physical limits like heat and power consumption are constantly pushing back.
Yeah, that's the constant battle.
And maybe how does that ongoing challenge then shape the very way software has to be written to take advantage of it all? Something to ponder, perhaps, next time you click an icon and wait just that moment for something to happen.